The first chi-squared test that I want to talk about is called the goodness of fit test. And this is a test that's going to be able to tell us how good a statistical model is at fitting the data. And so the example that we're going to go through will deal with an election. So the idea when you do polls is you want to come up with a statistical model of how are people going to vote in any given election. And then you can run samples and say, do these samples fit the model? And that'll either give evidence that the model is correct, or we'll have to go back and we can try and come up with a better statistical model to try and predict what's going to happen. So we're again in the land of inferential statistics. The way that this is going to work for the goodness of fit test is you're just going to have basically one category. So I think an election is a really good example in this case. You just want to know, go up to a random Missouri voter and say, are you going to vote for the Democratic presidential candidate, Republican presidential candidate, or someone else, a third party candidate? Third party meaning not Democrat and not Republican. And really, those are the only options. And from that, what you can do is say, is this going to be a good model or not? So you can come up with these numbers, figure out whether it's going to be a good model or not. The way that this is going to work is that we're going to let n be the sample size as always. P is going to be the list of probabilities for the values in the null hypothesis. So explain what that means as we go through the example. And then the expected frequency is going to be the sample size times the probability for the value. So it'll be E equals NP. Okay, and so again, we'll make sense of that formula soon, but that's going to be what's called the expected frequency. We're going to let capital O denote the observed frequency, and we're going to assume that we have lowercase c observations made. So in our case, if we're talking about Democrats, Republicans, or others, there's basically three categories, okay? So when I say number of observations, I don't mean sample size. I mean, this is the number of options that we're giving the person taking the poll, okay? So in our case, if we had Democrats, Republicans, or other, we would have c equals 3. The test statistic is going to be determined by adding up this quantity. So you take the observed value minus the expected value and square it, divided by the expected value. And then you do that for each of the different categories. Okay, so we had 3 categories for our example for the poll. So we'll do this 3 times. When you add up that value, you get what's called the test statistic for the chi-squared distribution. And this chi-squared distribution will have a degrees of freedom being c minus 1, where c is the number of categories. So in our case, for our example, if we have Democrat, Republican, or other, we would have c equals 3, because we have 3 categories, and therefore 2 degrees of freedom. Okay, the way that this is going to work when we do this as a hypothesis test is that the null hypothesis is always going to be that the observed data fits the model. The alternative hypothesis is that the data does not fit the model. And we can use either a critical value approach or a p-value approach, whichever you prefer. I really like the p-value approach because I feel like R is super useful in this case. I feel like R is super useful. It has been super useful since about chapter 5. And so it gets even more and more useful because these are more and more labor-intensive calculations as we go on in the course. And so if we know how to use R properly, then that can save us some time and energy. So what I want to do in this video then is to go through and by hand solve this problem, this example, and then I'll show you how to do the same problem in R. So we'll walk through that. We'll walk through both of those together in this video. Of course, we'll reach the same conclusion. But anyways, we're getting ahead of ourselves. So let's do this by hand first. And let me just read the problem, and then we'll talk about how to tackle it. So the idea is that data from the 2016 election reveals that there were 1,594,511 Missouri voters that voted for the Republican presidential candidate. 1,071,068 Missouri voters voted for the Democratic presidential candidate, and 143,026 voters voted for a third party candidate. These are real numbers, by the way. In the 2020 election, a sample of 300 likely voters were asked their voting preferences as far as whether they were going to vote in the 2020 presidential candidate, 2020 presidential election, whether they were going to vote for the Republican candidate, Democratic candidate, or a third party candidate. And so there were 300 people polled, And of those 300, 171 said that they intend to vote for the Republican candidate, 124 intend to vote for the Democratic candidate, and 5 plan to vote for a third candidate. What the question is asking now is, does this sample, does this poll give us enough evidence to say that the political makeup of the state is different than it was in 2016? So remember that the null hypothesis, in general, the null hypothesis is that nothing happens. Um, Specifically for a goodness of fit test, the null hypothesis is that the data fits the model. In other words, it's a good model, nothing interesting happens. What we expected to happen happens. So again, just in general, the null hypothesis is that nothing interesting happens. The alternative hypothesis is that we have something new. So in our case, the null hypothesis is that the data fits the model. It's true that this is our null hypothesis in our case. It's also in every case. I should say it like that. So the null hypothesis is that the data fits the model. The alternative hypothesis then is that the data doesn't fit the model. Okay, and so what we have to do now is we have to come up with the expected turnout that we would have using the 2016 numbers, compare that to the observed values of our sample, and then that's how we'll calculate our chi-squared test statistic. So what we're going to do, is we're going to make a little table here. And before we make a table, I think it'll be useful to take 1,594,511, 594, 511, and we're going to just kind of keep track of the counts of votes for the Republicans, Democrats, and others in 2016. So this will be our 2016 data. So then we had 1,071,068. And then for the third party candidates was 143,026. Okay, so that's our 2016 data. And then what I want to do with that is I want to use that to be able to make predictions. And so what I'm going to look at is the relative frequency of each of these. So I'm going to take each of those numbers and divide by the total number of voters that voted in the 2016 presidential election. And so that's going to give us our relative frequencies. And it turns out that if we go back and just look at our problem here, it turned out that in 2016, let me record it this way. In 2016, 56.77% of voters voted Republican, 38.13%, so 38, it's actually 0.135, so it's 0.14 percent voted Democratic, and there were 5.09% that voted other. Okay, and so these probabilities add up to 1. And what we're going to do with these is we're going to come up with, we're going to use these relative frequencies, come up with what do we expect to happen in 2020 using the 2016 model, and then we'll compare it to our sample and see if anything has changed. So our expectations, so let's look at Republican, Democrat, and other. Our expectations are going to be these values times, if we have a sample of 300, we would expect 56.77% of 300, which is 170. I'm going to call it 170.3. We would expect that many people to vote Republican. We would expect 114.4 to vote Democrat, and 15. I'll just call it 15.3 to vote other. That's what we would expect using the 2016 model if we had a sample of 300 people. Now, the actual sample of those 300 people found that we had 171, 124, and 5. Okay, those were the actual numbers as compared to the expected values. And so now what we can do is we're going to take each of these values, we're going to take the observed minus the expected, square it, divide by the expected. So this will be 171 minus 170.3 squared over 170.3. We'll take 124 minus 114.4 squared divided by 114.4. And then we'll take 5 minus 15.3 squared over 15.3. These values, when we do that, what we're going to end up with, um, if we just plug this into a calculator here, what we're going to end up with are, we need to write down our observed numbers here. This will just take a second to plug into a calculator, but what we end up with, when we add all of these up, so let's see, we're going to end up with, this is 0.0027. I'm just going to go to 4 decimal places. This is 8.046, and this quantity is 6.9137. And then our test statistic that we're going to get, which we'll call chi-naught squared, is going to be the sum of those values. And if we add up those values, what we're going to end up with is 7.721. Okay, so that's going to be our test statistic. And so what we're going to do at this point is we can use R, or we can use the table to actually look at what is the critical value. And so we want to look at, we're going to look at, let's see, the chi-squared value for 0.05. Did I mention a statistical significance here? I meant to. Let's just say that our we're looking at 5% statistical significance. We have 2 degrees of freedom, and it turns out that our cutoff there is going to be, so our cutoff there is going to be 5.99. So if we were to look at our critical value, there's 2 ways that you can calculate this. I'll explain both ways in a second, but the critical value is going to be 5.99. Okay, and then what we're going to do at that point is compare it to the test statistic. And our test statistic was 7.721. That's greater than the critical value. And so what that means is that we're going to, reject the null hypothesis. So we reject the null hypothesis. In other words, yes, we do have enough evidence that the political makeup has changed. Okay, so the political makeup has changed. Okay, and so that's how we do this by hand. And again, by hand, I know I used a calculator, but I mean, that's how we do that without R. And what I want to do is let's show 2 other things here. So I want to show you how you come up with that critical value using R, and how you come up with that critical value just using the table. And so let's jump over, and I will show you first the table. This is the table that I linked to in the handout there. This table here has the different p-values. We had a 5% significance, so by p they mean the significance. In other words, that's our alpha. And we had 0.05 as our alpha. We had 2 degrees of freedom, so that was 5.991 was our critical value. Okay, so that value there is how we got our critical value of 5.99. All right, now the last thing that I want to do is I want to show you how to do this in R. And in R, what I'm going to do is I'm going to try and get both of these up on the screen at the same time. So let me show you, let's do it this way. let me show you the problem, and then I'll try and have R on top of that. So, okay, here's the desktop. And what we're going to do is, again, we're going to look at our data. I'm going to have R up here just to show you how we can use R to do all this. And the way that we're going to do this in R is we're going to use the chi-squared test function. So remember that if you ever forget some of the details, you can always just use the help chi-squared.test function. That'll come up with this R help box that gives you basically all the details that you need about the chi-squared test function. And so what we're going to do is I'm going to store the 2016 data in that we had 1,594,511 Republican voters, 1,071,068 Democratic voters, and 143,026 third-party voters. And if we want to turn this into the relative frequency, what we can do is we can take this data and divide each number by the sum of the data. And that's going to turn it into this relative frequency term. These are basically the probabilities that a randomly selected 2016 voter would vote Democrat, Republican, or third party. That's where the 56.77% came from in the videos. And from this, we're going to look at the observed values. The observed values were, let's see, from our sample of 300, our observed values were 171 Republican, 124 Democrat, and 5 third party. And then what we can do is we're just going to use the chi-squared test. So chi-squared.test. We're going to use our observed values as compared to our relative frequencies. So this p equals means this is the vector of probabilities that we have. So our probabilities were the relative frequencies here. And again, just like in the last chapter, we're going to turn off the correction value. And so this is the code for the chi-squared test. And it turned out, so this spits out our chi-squared value 7.721, which is what we found. We, of course, had 2 degrees of freedom. And this calculates not only that, but also a p-value. Our p-value here was 0.02106. So if we had a significance of 5%, our p-value is smaller than that, so we reject the null hypothesis. I also want to point out in R, you can use R to calculate the critical value. And the way that we do that, since there's no symmetry anymore, you have to think very carefully about what the code is going to be, but you want to come up with, oops, this should just say Q chi-squared. You want to come up with the cutoff value so that up until that value is 95% of the data. In other words, after that value is 5% because the total area under the curve is 1, and you have 2 degrees of freedom. So that's that 5.991 value that we found in the chi-squared table. Okay, so this is how we solve the problem using R. We previously talked about how to solve the problem doing this by hand, but I hope that you agree that knowing and understanding R makes our lives easier. Okay, this makes the problem much more reasonable. In the next video, we'll talk about different chi-squared tests.